Welcome to our video series on residual stress. In this section, we will be introducing the basic concepts of residual stress. What is residual stress? To understand residual stress, you must first understand what stress is and how it is distributed in a material. Stress is created when a force is applied across an area. Stress is represented by the Greek letter sigma and is measured in megapascals or thousands of pounds per square inch. Stress is equal to force over the cross-sectional area of an object. There are two types of stress that can develop inside a material: normal stress and shear stress. Normal stress is designated with the Greek letter sigma, and it acts perpendicular to a plane or face. Shear stress is designated with the Greek letter tau, and it acts parallel to a plane. At any point inside a material, we can visualize a small cube. It is possible to have 3 stresses acting normal to each face, and also shear stresses acting across a face in 2 directions, resulting in 9 stress values: 3 normal, and 6 shear. For a static object, pairs of shear stresses must be equal, resulting in only 6 independent stresses. The subscripts indicate the direction of the force and the face it acts on. How are stress and strain linked? Strain is a measure of how much a material has stretched or deformed. Strain is often easier to measure than stress. Strain is equal to the change in length over the original length. A material subjected to stress will deform elastically until it reaches its yield point, meaning it will revert back to its original shape when it is no longer under applied stress. However, when the yield point has been surpassed, deformation becomes permanent. Take an elastic band. When being stretched, if the elastic band does not reach its yield point, it will return to its original shape after you let it go. If you stretch it beyond its yield point, you will notice deformation. Eventually, when stretched too far, the elastic band will break. Residual stress is the internal stress distribution locked inside an object after all external loading forces have been removed. These stresses are the result of the material obtaining equilibrium after it has undergone plastic deformation. There are 3 types of residual stress. Type 1, macro, is the average residual stress over a group of grains in the material. Type 2, micro, is the residual stress between grains. Variations may result from different phases in the material. Type 3, submicro, is the residual stress within one grain. Variations may result from dislocations or crystalline defects. How exactly does residual stress affect part fabrication? When the raw materials are manufactured into the final product, there are processes along the way: heat treating, forging, machining, and surface enhancement. Each process adds residual stress to the final product. Why do these processes create residual stress? There are 3 main ways in which these processes can create residual stress: thermal processes, such as solidification of a material in a cooling casting; machining processes, such as plastification of a material during machining; and phase changes, such as precipitation or a phase transformation resulting in a volume change. We must also consider the applied stress in a component. The applied stress could be of a similar magnitude as the residual stress, making a significant impact on the part during service. The total stress is equal to the residual stress plus the applied stress. Did you know that compressive residual stress helps reduce total stress? Compressive residual stress pushes a material together. It is generally favorable and can increase fatigue life and slow crack propagation. Why does residual stress matter? Residual stress is important because it determines the fatigue life of a part, its resistance to corrosion, the effects of distortion, and the dimensional stability over time. We hope you enjoyed our video on residual stress. Thanks for watching!